Good morning. Today we are going to discuss about strength of concrete, that is the hardened properties of concrete. Today we are going Good morning. Today we are going to discuss about the hardened properties of concrete. If we take the hardened properties of concrete, the first property which we are going to discuss will be the strength property. Strength of concrete, and we all know that concrete is a bonded particulate matter, and all the bonds are mainly due to van der Waals force. We all know that concrete is a bonded particulate matter, and all these bonds are largely because of the mechanical bonds. So if we pull the concrete, we can break these mechanical bonds easily. Rather, if we push them, it will take lot of loads. That is, if we push it, it will be much stronger and it will take much load. That is, if we push the concrete, if we push the concrete, it is relatively stronger and it will take much load. And in the strength property, we will be mainly discussing about the compressive strength of concrete. Again, this compressive strength is nothing but the cube compressive strength of concrete. Why do we need this cube strength? What's the need of this cube strength, and how do we determine this cube strength? These things we will be going to discuss in this lecture. This cube strength is mainly used for the strength of concrete is estimated through this cube strength, and this cube strength is mainly used for design purpose, and this cube strength is determined through experimental process, and this cube strength is determined through specimen testing, and the determined strength depends upon specimen type and test conditions. So for a structural design, I should need the strength of concrete. To determine the strength of concrete, I should have done test on the cube strength, and based on that cube strength, I will be getting the values which I need for the structural design, and that cube strength value depends upon the specimen type and the test conditions under which I am testing the specimen. In the specimen type is nothing but the compression strength of the specimen type is nothing but the compressive strength of cylindrical specimen will be lower when compared to that of a cube compression strength of the same concrete, and again these values will be lower than that of the in situ concrete, that is concrete made in a laboratory, and if it is cast in a cylinder specimen and a cube specimen, and if I test both the specimens, the cylinder specimen will give me a less strength when compared to that of the cube, and the same concrete, if I do it in a site, that concrete will give me a different value. So that is the specimen type, how the specimen is being casted, where it is being casted, based on that my values will be differing. The in situ strength can be related to cube strength, and cube strength can be a relative measure of the mix. Since I am making a concrete based on the mix proportion which I arrived, so it is a relative measure of the mix proportion. So based on the mix proportion, I will be getting some values. So I can relate the strength to the mix proportion. So the cube strength, if I test a concrete made in a in situ, so I am testing cube strength, I am preparing separately, and I am not taking it from the structural value. Cube strength, I am for estimating the cube strength, I am preparing separate cubes, and I am not taking it from the structural value. And for structures, again I am casting it separately, doing it separately. So this cube strength, it is a relative strength potential of mix proportion. So this cube strength is a relative strength potential of the mix proportion which is going into the concrete. Based on that, I am getting a strength value, but I have to use these values while designing a structure. So I have to correlate this cube strength to the design purpose, and we can relate the cube strength to that of the design strength through some means, so that I can use the values in the structural design purpose. So for a structural design purpose, the concrete which I am using is basically derived from that of a cube strength value, and through some means I am correlating it to the structure design purpose. The strength of, when I refer to the strength of concrete, it obviously refers to the cube compressive strength of concrete, and in that the cube compressive strength of concrete, the values for structural design is being achieved by connecting the cube strength and the structural design strength through some means. And the compressive strength of concrete depends upon three factors. First one paste strength, interfacial bonding, and third, aggregate strength. In a normal concrete, the concrete specimen will fail through the aggregate boundary, and the aggregates will not fail in a normal concrete. Supposing if I am testing a cube, I am testing a cube specimen. In the cube specimen, I am applying load on both the faces, and after applying my load, if I study the failure pattern, the failure pattern will be somewhat like this. If we study the failure pattern of the cube, we can see that the aggregates are being exposed and the failure is through means of aggregate boundary. That is, the failure would have happened because of the failure in the aggregate boundary and not because of the failure of aggregates. This is how the normal concrete failure takes place. If it is a high strength concrete, then there would have been a crushing of aggregates. Now, for a normal strength concrete, the boundary failure will be the main reason. The aggregate boundary failure will be the main reason for the failure of the specimen. This three phases, the three factors, the compressive strength, as I told you, the compressive strength depends upon three factors: paste, interfacial and aggregate strength. Suppose this is a matrix, here my aggregates. This is my hydrated cement paste. This is my aggregate. And there will be a boundary between the paste and the aggregate, and that is called interfacial transition zone, ITZ. And the failure mechanism, if we observe the failure mechanism of a normal concrete, we can find the failure would have take place in this ITZ zone. This paste phase, the boundary between the paste phase and the aggregate phase is called the interfacial transition zone, ITZ. So, if we come to this paste strength, the paste strength, how do this paste strength is attained. The space strength is attributed the space strength is obtained because of the cohesion between gel particles. Because of this cohesion between gel particles, that is nothing but the van der Waals force which we discussed in the first lecture, because of that the paste strength is being achieved. So the cohesion between the gel particles is responsible for the paste strength, and if we break the bond between them, the paste strength will be reduced, and if we break the cohesion bond between the gel particles, the paste strength will be reduced, and there a large discrepancy exists between the theoretically calculated paste strength and the actual paste strength which is being exerted by the concrete, and this discrepancy is mainly due to the flaws that exist in the actual concrete. Theoretically, I can calculate the value, but actually while making a concrete, if there is any flaws, then that flaws plays a main role. Here in the failure mechanism, how do a crack get initiated? That is the main point. From where my crack is getting propagated, from where my cracks are getting started when I am applying the stress. So supposing if there is a initial flaw in my structure, initial flaw in my concrete making, that remains the same throughout the entire lifespan of the structure. So when a load acts on it, the first crack will initiate from the flaw. So if suppose if there is no other crack, then the cracks will start, if there is no other flaws, then a crack will initiate from the gel pores. If supposing I am having a flaw in my material, then my first crack will propagate from the flaw which I am having in my material. So when a load is being applied, the first crack, supposing if I am having a minute pore here, then from there my first crack will initiate, then it will travel through the aggregate interface. Likewise, somewhere another pore might be there, and from there another crack will propagate, and finally they will form a network, and this is how a failure in a concrete take place. So the space strength is due to the cohesion between gel particles. So a theoretically calculated paste strength will have a much higher value when compared to the actual paste strength. That is because mainly of the flaws present in the materials. This interfacial bonding is nothing but the ITZ. If supposing this interfacial bonding is nothing but the boundary present between the paste and the aggregate, and if there is any and this ITZ has a different property than that of the cement paste and the aggregate, and this interfacial bonding when ruptures, then it leads to failure. 30 micrometer thick, this interfacial bonding. Next, aggregate strength, and this aggregate strength based on how we are choosing the aggregates for the concrete making. Based on that, our strength values will vary. Either it will vary due to the paste strength, or because of the interfacial bonding, or because of the aggregates chosen. Next, failure of concrete. Till now we have discussed about how the strength for a structural design is being calculated. That is being calculated by means of cube strength, and that strength value again depends upon these three main factors. Now, how a failure of concrete take place when a load is being applied. Assuming it to be my cube. If suppose I am applying load like this, that is, if I am applying tension to my cube, then the concrete will fail like this. If I apply a tension force to my cube, then the crack will form like this, and as I told you, that crack propagation will take place from the flaws present in the material, and from there it starts developing, and when finally they form a network, the total collapse will take place. This failure pattern is observed when we apply uniaxial tension. If supposing I am applying uniaxial compression to my specimen, then how my cube will behave. Here I am applying load, here I am applying load. When I am placing it in a compressive strength testing machine, the platens will be holding the top and the bottom surface of the cube, and load will be applied. Then there I will be observing cracks in this manner. That is, when I am pressing the material like this, it is free to move in the other direction. So, I will be observing the vertical sort of cracks. If I supposing I am applying load in both the direction, biaxial direction, then again the material will tend to move in the other direction. I will be developing cracks in this manner. This is uniaxial compression, and this is biaxial compression. If supposing I am applying load on all the three sides, now how the material will behave. Here when I am applying load on all the sides, compression on all the sides, the gel pores will try to reduce in size. That is, the materials will try to shrink. The gel pores, if suppose anything is being present, it will try to compress from all the sides, and it will take more load. So, and that's the reason why we tell that concrete is strong in compression and weak in tension. If supposing in well, I am applying a tensile load, it can easily break because of the already being present flaws, and from there I am trying to pull the material, so it can easily break. Whereas in compression force, I am trying to push the material so that even any gel pores present will try to compress in size, so that I can it can take more load comparatively, and that's the reason why we are telling that concrete is strong in compression. And how this crack growth, how, if supposing I am applying uniaxial compression, why the cracks, why the vertical cracks are being formed like this, what's the reason behind this is, even though the applying load is of a compression type, the material will fail in tension. That is, I am applying compression in this manner. I am applying compression in this direction. So my material is free to move in the opposite direction. So the failure mechanism is not really because of compression, but by tension in the transverse direction. So this is how, because of this only, I was able to get a concrete failure in this manner. Because of this reason only, the failed concrete specimen which I obtained was in this shape. This is the reason behind it. Even though I am applying a compression load, the failure mechanism is because of the tension in the transverse direction. This is all based on this specimen type. The specimen type, how either we are using a cylinder or a cube, and based on that the cube strength will vary. In the next lecture, we will be discussing about the test conditions.